Hello, everyone. We are going to start section 2.2 today, evaluating determinant by row reduction. We already know how to evaluate determinant by row expansion, and for bigger matrices, it can be a very, very long work. We're going to learn another method of finding determinants. Before we do that, we'll need to go through certain theorems. We're going to start with theorem number 1, and that's going to be next one. Some of them are going to prove, some of them are going to be obvious. Theorem number 1, if matrix A, square matrix A, has a row of zeros or a column of zeros, then determinant of A is going to be equal to 0. Yes, I'm not going to prove this theorem, but you just imagine that you have a row of zeros. You can always use this row of zeros to expand the determinant, and then you are going to have all zeros in that sum. All right, so kind of clear. Next theorem. Theorem number 2. Determinant of transpose matrix is going to be equal to determinant of original matrix. Well, here maybe I'll say a few words about that. Imagine that I calculate determinant of this matrix, determinant of matrix A, as expansion by the first row. So A11, C11 plus A1n, C1n, right? Now, a transpose matrix is going to have this first row as a first column. Let's imagine that I'm going to use expansion for transpose matrix as, I'm going to label here, expansion by first row. And here I'm going to expand by first column, which is also going to be the first row. So I'm going to get again A11, C11 plus all the same elements 1n, C1n, expand by first column. Yeah, you probably will tell me, well, these C's are probably not going to be the same C's just because we kind of going to calculate C's of transpose matrices, right? Because all of these smaller ones are also going to be transposed. Yes, that's correct. But if you consider determinant of like, I don't know, the smallest matrix 1, 1, if you do transpose of it, that's going to be the same, right? You understand that the C's eventually will go to that very last one, which is going to be the same determinant because the matrix of one element transpose is the same matrix. You can try to check this on 2 by 2 matrix. You are going to see that it's going to work. And well, again, because the formula is recursive, eventually, like this is step number 1, right? When you start doing the determinants. On the next step, you are going to, of course, have like these C's are going to go through direct matrix. These are going to be transposes, but still they are going to be like kind of determinants of transpose. And again, they are going to be equal using that same formula. Just like remember that determinant of 1 by 1 matrix and determinant of 1 by 1 transpose matrix is going to be same, and that's just going to be element 1, 1. So this C's Well, in general, not supposed to be equal to these ones because they are going to be C's of transpose matrices. But again, because you're gonna go down, 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 and eventually gonna hit this one, they are going to be equal. Okay, I don't want to go in like very deeply into that proof. Usually, you can prove it by induction. Just compare like two transposed first matrices and the second 2 by 2 matrices transposed also. Okay. Now, guys, well, remember that the topic of our section is use row elimination, right? And let's talk how operations on matches, row operations, elementary row operations on matrices are modifying the determinant. So next theorem is going to talk about like what row operations are doing on the determinant. And that's going to have three different parts. Part number one, if B is obtained from A by multiplication by constant number of any row or column or row, then determinant of this new matrix B is going to be K to the power of n, determinant of all matrix A. Oh, not to the power of n, sorry. Sorry, determinant just K. Second, if B is obtained from A by interchange of two rows and also columns, then determinant of B is going to be just minus determinant of A. And the last one, what we can also do to the last elementary operation is if B results from addition of two rows or columns, then yeah, I'm writing it short, but we remember that actual operation is multiply one row by any non-zero number and add it to another one, right? Well, for that operation, determinant is not going to change. Determinant of B is going to be equal to determinant of A. So this is the safest operation, does nothing to determinant. Well, the first operation is multiplying determinant by K. The next operation is changing the sign, and this one is doing nothing. I'm going to prove a couple of them, and I'm not going to prove like maybe one of them. So, proofs. I'm going to start with number one. So I'm going to write down, I'm going to multiply by K first row. It does not matter, but if I want to use my formula, I'm going to multiply by K the first row, and all other rows are going to stay the same. And I'm going to calculate the determinant of this and expand by the first row. Well, you probably already see what is going to be the result. So K, A11 by C11 plus K, A1n by C1n. The rest of the matrix does not know anything about multiplication, so all C's are going to stay same. The only difference is going to be that we are going to have extra K factor in front of each term here. So we take it outside. We are going to just get a standard determinant of matrix A. So that's going to be K, determinant of matrix A. But the proof of the first part was kind of easy. Proof of the second part is going to be more complicated, and I'm not going to do the whole proof, but I'm going to show you like why it works. Well, I'm going to consider like standard matrix A11, A12, A1n, A21, A22, A2n, and I'm going to just write lots of dots over here. Imagine, guys, that we switch row number 1 and row number 2. What is going to happen to the formula? Well, if I put row number 1 in the position of row number 2, uh, what is going to happen to the formula? Remember that we do have this checkers word rule for the signs of like minor multiply, the signs of cofactors. So if I place all my elements of the first row in the second row, they are still going to stay like elements like 1, 1, right? But each cofactor is going to get extra minus 1 in front. If it was positive, it's going to become negative. If it was negative, it's going to become positive. And so on. And all of them are going to have this. And that's going to be the major result. Like, why do we have it's negative, right? So it's going to be minus determinant of matrix A. And everything looks good, right? Change of the first row and the second row, you are going to get the minus. And again, the minus happens because all these minuses are going to happen here, like instead of pluses. And when you cross out this first row and start doing these cofactors, the rest of the matrix is not going to even know like that you did the switch, because for the rest of the matrix, everything is going to look like it was original matrix over here, like as below first row. Now, guys, well, it's not always necessary to exchange row number 1 and row number 2. What if you exchange row number 1 and row number 3? 1 and 3. Well, for row number 3, actually, the signs are going to be exactly the same, right? So we're not going to get this extra 1 minus 1 in front of all elements of this, just because you place them in this like third position, because the sign is same, plus, plus, minus, minus, minus. Right, guys. But when you go into minors now, for minors or for cofactors, the matrix is going to look like you have the second row. Oh, sorry, not the second row. It's going to look like I'm going to do like draw the matrix for cofactors. For cofactors, the first line, when you cross this number 3 to do cofactors for it, the first line is going to have row number 3, and then row number 2, and then like skipping row number 1, and then 4, 5, and so on. You see, for this matrix, for cofactors matrix, there is going to be an exchange between 3 and 2. And this exchange, when you calculate the determinants, is going to give you extra minus just because you are exchanging like positive and negative positions. Like, and it does not matter whether 3 or 2 are like, one has pluses, one has minuses. We don't really care which one has pluses, which one has minuses. This one has pluses, this one has minuses. Okay. If this one has minuses, this one has pluses, also okay. And so we are again going to have minuses. Just these minuses are going to come from inside of these cofactors, not from like literally minus and plus, which you use when you multiply minor by them. And of course, there are more complicated situations, like when you exchange some rows in the middle, but eventually you are going to get these minuses either directly from like this checkers board or non-directly by going inside, just because this is recursive formula. I'm not going to do the full proof, kind of gonna take lots of time. You can kind of think about this proof in this way. A little addition to this kind of proof, extra conclusion. So guys, when I exchange two rows, I'm going to change the sign of determinant. But if I have two same rows, if A has two same rows, then when I exchange them, on one side, nothing is supposed to change, right? So determinant is supposed to stay. So determinant of matrix B is supposed to be equal to determinant of matrix A if you have two same rows and you exchange them. On the other hand, when you exchange two rows in a determinant, according to this rule, it's supposed to be equal to determinant of like minus determinant of matrix A. Well, it looks like determinant of matrix A must be equal minus determinant of matrix A, but it's a number, right? A equals minus A, which is supposed to be only one number, 0, because all other numbers are not equal. Like 1 is not equal to minus 1. 0 is equal to minus 0. So, important conclusion. If matrix has two same rows or two same columns, determinant of that matrix is equal to 0. Same as determinant of 0 column. Okay. And the last one is kind of going to be longer. Last one is describing operation of multiplication of one row and adding it to another row. And that's going to be a little bit longer, but the proof is very interesting and maybe you guys will like it, even like it's using a little trick. Okay, for proving of the third one, let's imagine you can multiply it by any number, but I'm going to do a simplest operation. I'm going to take row number 1 and add row number 2. You will see 1, 2 plus a 2, 2, and you will see how it works, and you probably will understand what is going to happen if you multiply by a constant number, this second row. And I'm going to keep second row itself and the third row also. Sorry, keep switching indexes. And like, that's my matches. Now, guys, I'm going to use expansion by the first row, and that's going to give me A11 plus A21 by C11 plus, those C's are not going to know that you did this separation on the first row. Why? Well, because the rest of the matrix is not disturbed by this separation. A1n plus A2n and C1n. Well, I'm going to open parentheses and have A11, C11 plus like lots of terms, A1n, C1n, and plus A21, C11 plus A2n, C1n. Well, everything is clear with this part. That's just determinant of matrix A, right? Like you expanded it by the first row. What is going to happen with this part, guys? What you have minors or like cofactors actually. Cofactors and minors are going to be inside. You have cofactors of the first row and you multiply them by elements of the second row. Well, for us, it's going to look like you are calculating determinant of the next matrix. And then these cofactors are cofactors like of this remaining matrix, which are like not remaining, but like, 2, 1, 2, 2. They are going to be obtained from that matrix. And of course, it's not going to be the whole thing. You are going to cross either first column or second or whatever, but the numbers are going to come from the matrix. And other elements, 3, 1, and so on. Okay, so you see what happens here. You have row number 2 sitting here, and you have row number 2 sitting here. So this is determinant of the matrix with two same row number 2. this determinant, I'm going to label it as matrix, I don't know, A star. It's going to be equal to 0 because the matrix is going to have two same second rows. Well, what is going to happen if that's not a second row? Well, then it's going to have two same third rows or fourth rows or fifth rows. Just when you add the row over here, it's going to repeat one of the rows below and automatically going to give you a determinant of a matrix with two same rows. What is going to happen if you multiply a row by something? Here, I did not multiply by anything, but if you multiply by a constant here, like constant here, well, you're just going to have a constant everywhere and you can always take it outside. But because determinant is going to be equal to 0, this outside constant is not going to affect it. And you see that the whole determinant equals 0. So the final answer is just determinant of matrix A, which means that operation number 3, taking a row, multiplying it by a number, adding it to another row, does not change determinant at all. So when you do row operations on matrix, you can use any of three operations, the first one, the second one, and the third one, accounting for either minuses or like getting extra number in front. But when you do the third operation, you don't need to worry about anything. So the third operation is the safest one, and you just if you do it all the time, you're not going to change anything. Well, I think I'll need to show one example how it works. And well, I don't wanna kind of be too long, but let's consider that's going to be example number 1, and matrix is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, guys, I'm going to do the same trick I was doing the previous time. I'm going to eliminate 3 and put 0 over here. So I'm basically going to have the very same matrix I had in the previous section. And I'm going to calculate the determinant of it. I know it's kind of boring, but you're going to see how the method is working. So guys, we remember from previous section that determinants of triangular matrices, upper, lower, diagonal, are just a product of diagonal elements, right? So we actually don't need to do full elimination, Gauss-Jordan elimination. We can just do forward elimination or Gaussian elimination. Turn this matrix into triangular or eliminate all elements below the diagonal, then multiply diagonal elements. And this matrix has just 3 non-diagonal elements. We just need to eliminate them. And that's after that multiply other elements, and that's going to be like diagonal elements, and that's going to give us the result. I'm going to start doing this, and it's going to take some time. I'm sorry, guys, the boring process in front of you. You can skip it and just look at the final result. So I'm going to start eliminating 4. I'll need to do row number 2 minus 4 row number 1. And to eliminate row number 3, or 7 over here, I'll need to take row number 3 minus 7 row number 1. I'm going to do these two operations at once. And my matrix is going to change like 1, 2, 0. And I'm going to get 0 here and 0 here, obviously, because I'm doing this on purpose. And if I multiply 2 by 4, I'm going to get 8. And if I subtract it from 5, I'm going to get minus 3. And if I multiply 0 by 4, I'm going to do nothing to this 6. The same, if I multiply 2 by 7, I'm going to get 14. If I subtract it from 8, I'm going to get minus 6. And with 0, I'm going to not change this 9. Very good. I already eliminated 2 of these elements, right? I just need to eliminate this one. Guys, usually when we do row elimination, we try to turn the element into 1. But remember that when we are doing that, we are changing the determinant. We need to kind of keep in mind that we are doing that and kind of account for this, like the first part of the theorem, right? I don't want to do this. So I'm not going to actually change element. I'm going to do row elimination without turning this minus 3 into 1. Again, by rules, I'm supposed to do that if I was solving system of equations, but because I'm just searching for determinant, I just need to eliminate minus 6, and that's going to be my final answer. And I see it's going to be easy to do if I multiply row number 2 by 2 and subtract it from row number 3, right? I multiply minus 3 by 2, it's going to give me 6 minus 6, and if I subtract it from minus 6, I'm going to get 0. Well, let's do that. I'm copying first operations. And this one is going to be 0 because I'm not. Now, if I multiply 6 by minus 2, I'm going to get minus 12. And if maybe I did a mistake somewhere. It doesn't look like I'm going to end up with a small number. I did that previous time, but okay. Uh, Yeah, I'm going to get a 12. If I subtract it from 9, I'm going to get minus 3. Okay. Well, now, guys, this is triangular matrix. Triangular, right? And the determinant of this matrix is going to be just the product of diagonal elements. Minus 3 and minus 3. And it looks like it's going to be 9. And guys, I don't remember if it was 9 before or not, but hopefully that was actually 9. You see, method is much faster than doing cofactors expansion. But again, you need to deal with fractions sometimes. This matrix was simple, relatively simple, and that's why I did it so fast. And I'm not even sure that it's supposed to be 9, but let's hope that it's supposed to be. Okay. Or let me double check it. Actually, give me a second. Okay, guys, I did check it's exactly 9 in that example. Very good. So two methods are matching, and you see that this elimination is not that bad. But again, it always depends on like what you see, like how many zeros you see in the matrix, how easy is going to be elimination. But again, you don't need to do full Gaussian elimination here or Gauss-Jordan elimination. You just need to do forward elimination, eliminate elements below main diagonal, and that's going to give you already kind of the answer. Okay, one more thing I want to talk in this section, and that's going to be last thing. What elementary matrices determinants we are going to have? Remember, we had elementary matrices which correspond to elementary operations. So I'm going to just calculate determinants. Elementary matrices, determinants. We'll need it for future. So let's start with same order of operations. So imagine that E n is resulting I n by multiplication by k, I don't know, any row. Any row. Which means how the matrix is going to look. Remember that identity matrix and elementary matrix, our matrix is going to look like this. I don't know like which row, but like row I, let's say. So we have 1, 0, 0, 0, here is 0, 1, and eventually on row I, we're going to have k, right? 0, 0 here. Well, because these are diagonal elements, determinant is going to be just product of diagonal elements, and that's going to be 1 by 1, and eventually you are going to have k here and then more ones, and that's going to be k. So determinant determinant of the first elementary matrix is going to be just k, whatever number you use. Exchange determinant, if E n results from row exchange. Well, we know that what row exchange is doing. It's doing the minus, right? But like if how my matrix is going to like look. Yeah. So I take identity matrix and kind of exchange row number 1 and row number 2. So instead of like 1 here from identity, I'm going to have 1 here. And instead of like 0, I'm going to have 1, and that's going to be. So this is exchange of row number 1 and 2. 1 and 2. I know that determinant of this exchange is supposed to be minus determinant of original matrix. My original matrix is identity. So determinant of identity matrix, it's a product of diagonal elements, which are going to be the product of ones, right? Because I exchange rows, determinant is going to be minus determinant of identity, which is going to be just minus 1. So second elementary matrix. And the last elementary matrix, well, determinant of last one, which is addition of another row. Remember that when we add another row, nothing changes for determinant. So it's going to be just equal to determinant of original identity matrix, which is equal to 1. So, well, we have like three different determinants for elementary matrices. One is K. The first elementary matrix is going to have determinant equals to K. The second one to minus 1. And the third one, determinant is equal to 1. Just going to remember it. We're going to use it sometime in future. Okay, that's all for this lecture. Sorry for my bad handwriting.